Okay. Now last time we talked about moment about an axis. Okay, now this is the formula. Okay. This formula is a scalar formulation. Okay, so this gives you the magnitude of the moment about, say, y-axis. Okay, in this picture, the lug nut example. Okay. So just refreshing memory, you have this wrench right here. Okay, and this is the lug nut, and then this is as if you're pulling it. Okay, straight up. So this is the force that you apply. Okay, now at this very instant, right, you have a force that's vertical, right? And then R vector is measured from the lug nut to the point of the force, where the force is applied. Now, in this picture, there are two moments to consider, right? So we can take moment about this point O, where the lug nut is, the origin of the coordinate system. And now we decided that if we take moment about point O, okay, this is a point that gives you m naught, but that's not very meaningful, okay, because lug nut can only travel in a certain direction, that is along the y direction. So to measure the effectiveness of this lug nut getting loose, okay, due to this applied force, my is more meaningful. Okay, that is taking moment about an y-axis. Okay, so this formula is fine. Okay, you can use this formula if you know the magnitude of force. Okay, whatever, how many newtons or how many pounds it is, and if you know this distance, that is the perpendicular distance, okay, between this point where the force is applied to the axis you're taking moment about. Okay, so either you know that or you know this distance. Okay, we'll call it d, right, from the previous picture, and then you know this angle right here. Right, then you can figure out what dy is. Simply d times cosine of theta. Now I'm going to introduce an alternative formulation. Okay, that's the vector formulation. Okay, now this vector form is useful if you don't know the magnitude of force itself, okay, or this distance right off bat. Okay, but instead you know the components, right, the x, y, z component of these guys right here. Okay. Now, recall that moment about a point is defined as r cross f. Right. So we've been doing this for a long time now. So now, this is this guy right here. All right. So just to emphasize the vectors. Now, look at this my right here. Okay. Look at this picture. My is closely related to this m naught, right? Look at this picture. M naught can be thought of as the total moment, okay, due to this force. My is a component of this m naught. In particular, it's the y component of m naught. Okay, it is a part of m naught. If you decompose m naught into this y, okay, direction, so you get this my right here. Okay. So if you look at this plane right here, right, this plane, the xy plane, right. So m naught is like the hypotenuse. My, okay, is the y component. You can subsequently also do mx, right? It's the x component, but mx is not meaningful. Okay, because lug nut cannot travel in the x direction, so it's not meaningful at all to discuss mx. So, knowing my is the y component, or the projection, okay, of m naught onto the y axis. Okay, so recall when we talked about dot product, the meaning of dot product, okay, is actually two vectors. Okay, you take one vector, project it onto the direction of the second vector, right, and then you multiply them together. Okay. So this is exactly what this is. So my is the projection of m naught onto the y direction. And using the definition of dot product, we come up with this right here. So my is this m naught vector, okay, moment about point O, dotted with the j unit vector. Okay, so j unit vector is right here. Okay, so a vector dotted with another vector gives you a scalar. Right, so this is a scalar, which is just a number. There's no magnitude. Okay, so dot product. Right, so your m naught vector dotted with the j unit vector. Okay, and m naught is this guy right here. So replace in here. So r cross f dotted with j. Now dot product, you can swap things around. So you know, a dot b equals b dot a. So move the j in front, and we can rewrite it this way. So my equals the j unit vector dotted with r cross f. Right? Again, r is measured from the lug nut, okay, the origin, to the point where force is applied. Okay, and f is just your force vector. Okay? We can extend this to any general axis. Now this is, take a moment about y axis in particular. Okay? So in general, extend this, okay, not just to y axis, but to any axis at all. It doesn't have to be x, y, or z. It could be any general axis. Okay? So moment of a force about any general axis A equals the unit vector u of this A axis. Okay, so let's say this is my unit vector right here, pointing along this A axis. So this is my u A, dotted with r cross f. That's it. So r cross f. Okay, so this mixture right here, okay, you have a dot product and you have a cross product, right? This is called mixed triple product. Okay, triple because you have three items here. You have three vectors. Okay, you have mixed because you have a mix of cross product and dot product. So you do the cross product first, and then you dot this vector, the resulting vector, with this other vector. The end result is a scalar. Okay? So, mixed triple product can be rewritten as this. Right? You can use determinant, okay, to help you figure out and do the calculation. Right? First row is the component of this unit vector. Right? So unit vector of A, the x component, the y and z component, same thing, and then the rest, you know, is just the x, y, z components. So this equation is the general equation for moment of a force about an axis.